Diffraction and interference are wave properties. You might have seen there's a tank with water in it. And so the waves coming this way. So these are wavefronts. So wavefronts are, how do you, so if you take the cross section of it, so these are the wavefronts. So that line to this line. So if you look at from the top, so this is a wavefront. And this wave is blocked by a wall, but there are two openings here and here. And what would happen is that when it goes through this narrow slit, and the wave will go like that. The wave is going to bend and propagate, and the same is going to happen here as well. So two things happen. These two waves are diffracting at this, because when they go through this narrow slit, and this is equal or smaller than the wavelength of this water wave that's hitting this wall, and so they're diffracting. And also you can see that two diffracted waves can interfere. So at these points, you can see that they are interfering in a constructive way. So what is constructive interference? So if you have a wave like that, and other wave is with the same wavelength and in phase with that, so what will happen is that resultant wave will be something like that. So that means the blue wave and the yellow wave are constructively interfering, and the resultant wave is this huge wave in red. So that's what's happening here, that the diffracted waves from both slits interfere, and there's a constructive interference. At the same time, there are some points they interfere destructively. So if you have a wave like that and another wave with the same wavelength but out of phase, so what will happen? The resulting wave will be like that. So they are destructively interfering. So let's write it down. So this is constructive interference, and this is destructive interference. So constructive and destructive. Talking about waves, this is something that is common for all the waves, so sound waves or water waves. So we're going to talk about diffraction and interference for light. So Newton, one of the greatest scientists, said that the light is consists of particles. So he said that when the light is traveling, it travels in straight line, and they are particles. So he will explain reflection of a light and refraction of light using his particle theory. But here came another scientist called Higgins, and he said, light is not a particle, but it's a wave. And he also explained the reflection and refraction using the wave theory. They both had the arguments for their own interpretation. But Newton couldn't explain diffraction and interference because he never believed that light is a wave. So Huygens was able to explain diffraction and interference using the wave theory. So he has this got theory to explain how waves propagate, the light waves propagate. So if you have a wavefront here, and what happens is that he explains that this is a wavefront. He said that every point in the wavefront is a source of another wavelet. Every point. So the next wavefront will be a tangent to all these wavelets. So that's of light propagate. So then we have got another series of wavelets, and tangent to those wavelets we got another wavefront. And if it's a circular one, then we have got the light would propagate like that. So if it's a point source, you would see the circular waves propagating like that. So he was able to explain diffraction because if you look at this point here, at the place where we have got the two slits, where the water waves are diffracting, and he argued that the same happens for light. So the light waves coming here, and the slits, the size is smaller than the wavelength or equal to wavelength, so the light diffracts. And because it's a point that is a source of another wavelet, and then the light would propagate like that. So he was able to explain the diffraction of light using his the wave theory. So although Huygens was able to explain what diffraction is and how interference works, and he was able to explain it in a qualitative way, but here come another scientist called Thomas Young. And he did an experiment called double slit experiment, and in which he was able to prove quantitatively how the diffraction works. And he was able to convince the world that light is actually a wave. So this is what an experiment similar to what Young did. So we got this monochromatic coherent wave and going through these two slits, and these wavefront, and at point sources they become wavelets, and they are being propagated from both slits, and then they are interfering with each other, so that we have got these dark and light spots in different places. And the central place here, you see a light spot, and there's a light spot where we say n is equal to 1, 2, 3. So these light spots are called antinodes or antinodes, or there's another way to say it is the maximum. So this is the zeroth maximum, first order maximum, and the second order maximum, and third order maximum. And these ones is actually showing the intensity of these waves at these points. So the intensity is quite high at the midpoint, and then it's being reduced a little bit. And if you look at these ways, so what we are going to look at is that how the distance from the central maximum to the first order maximum and third order maximum, how they are affected by this length, the length between the screen and this optical screen where we have getting the image, and also how is it affecting the angle. And also we will look at, like, if we send a particular wavelength, and what would be the distance. So by measuring this distance, we will be able to find what's the wavelength of wave. So this experiment has got lots of variables dependent on independent variables, and we can find out the dependent variables by using this experiment. So this is the screen with two slits, and this is a screen that we see the result of the constructive and destructive interference. So this is the first order maximum where we see the first constructive interference from the midpoint. So we call this central maximum, or we can call it zeroth order the maximum, or this is the first order maximum. So these two waves are constructively interfering, but their path length are different. If you look at the path length of this one and this one are different, but they can constructively interfere only if the difference is the multiple of the wavelength. So say for instance you have a wave like that, and there's another wave going like that. So in this case, I didn't draw it properly, but if you assume the wavelength of two waves are the same, the path length is this. This is L1 and this L2. And if you look at this, the path lengths are meeting at this point. That means they are destructively interfering. If you look at the point, corresponding point, there's a peak here and there's a peak here. So the path lengths are different. So that means L2 minus L1 is equal to, we can say it's a multiple of lambda 2. Because if you want to make two waves to interfere, that means a wave going like that and another way going like that. So they are constructively interfering, although their path lengths are different. So in that case, we can say if this is L2 and this is L1, that means L2 minus L1 is equal. So you can say n lambda, because it should be a multiple of lambda. It could be 0. That means the both wave are the path lengths are the same. And if it is 1, that means the difference between the path lengths is 1 lambda. So the path length between those two lines, so this is a wave and this is a wave, and obviously the path lengths are different. So the path length difference between those two is this part. And let's say that's small delta. And this angle is theta and this angle is theta. So that means this is equal to d sine theta, because this is theta. So this is d sine theta. And one assumption we are making is that this line and this line are parallel, because compared to this distance, the distance between the slits, and this length is bigger. So we are going to assume that they are parallel. That's the reason we are saying this delta is equal to d sine theta. So let's write that down. So delta is equal to d sine theta. And as we discussed before, that if these two waves are constructively interfering, we can say that delta is equal to n lambda. So delta is equal to n lambda. Remember that sometimes they use m for n. So as long as you know that this is the one giving the order of the maximum. So when n is 1, that's the first order maximum. When it's 0, it's the central maximum. So we can write n lambda is equal to d sine theta. So because of this, the distance, the longer distance, and this is quite small compared to this one, so we are going to make an assumption that sine theta is equal to y over L. That is y over L. That's y and that's L. And that's also equal to tan theta actually. So we are going to replace that in that previous equation. So we're going to say, so n lambda is equal to d sine theta. So d is d times y over L. So this equation we can use to separate variables the way we like. Say for instance, if you want lambda is equal to dy over n, that's d pi over nl. So that means if we want to find the wavelength of a wave that's coming through to these slits, all that we need is that we find the distance between this central maximum and the first order maximum. We know this length, so, and we know the distance between these two slits. So we put the distance, and we know the distance between these two, the central and maximum one, and n is 1 when it's the first order maximum, and L is this distance. So we can find the wavelength, and if we don't have the wavelength, and if you know the wavelength and we want to find out y, then we can do that as well. So from here, we know y is equal to n L lambda divided by d. So depending on what is given and what we need to find out, we can always substitute the values in these equations and get the right answer. So by looking at this formula, you can see that if we are sending a wave with a bigger wavelength, so if the lambda increases, the y will increase. That means this will increase. So in this diagram, the distance between the two peaks, one is the central maximum and the first order maximum, will increase. And if d decreases, d is the distance between these two slots decreases, then also the y will increase. So the y is inversely proportional to d and proportional to lambda. So if we have the diagram, so the output of these two different waves, and so for one you have this one, and if you're going to send a wave with a higher wavelength, then obviously the resulting the output will have more distance between the peaks, and the same thing, that if d decreases, that will give the same results. And if you want to find the points for the destructive interference, instead of n lambda, we will have to do n plus half lambda, n plus half lambda. That means the original equation we wrote will become like d sine theta is equal to n plus half lambda. So that means that the path lengths are indifferent in the multiples of n plus half lambda. So n, if n is equal to 1, it's 1/2 lambda. If n is equal to 0, it's half lambda. So n will be 0, 1, 2, 3. So diffraction grating is when we have multiple slits. So the previously we used only 2 slits for the double slit diffraction, and the diffraction grating is like if you have a, so when we have multiple slits, what's going to happen is that we're going to have the constructive interference from multiple slits. So for instance, from here, so there's a wave going here, and another wave coming here, another wave coming here. So waves coming from multiple slits coming and merging, and there's a constructive interference. So that means this will be really, really bright spot here. And then you have, say, this one from here, from here, from here, and from here. And there's another bright spot. So diffraction grating is that you have a glass and then you have multiple slits. So it could be something like an engraving or some lines you draw for the light to go through. And so you have lights coming this way. This way, and they are diffracted, and then they are interfering at this place. So you will have multiple of this constructive interference. The what you can notice is that they are really, really bright spots. And one of the things that you can notice is that the conservation of energy. So all the energy that you provide here as light are concentrated on these, you can say antinodes or antinodes, or you can say the max points. We can use the same equation that we used before for the double diffraction. So we can say d sine theta is equal to n lambda. And d is again the distance between two slits, and the lambda is the wavelength. And we can use the same equation that we derive for the y, that is the distance from the central maximum to the maximum that we are looking at, and n is the number, the series, where which maximum we are looking at, is number 1, 2, or 3, and L is the distance between the screen and the slits, and D is the distance between two slits. So we can find the value of y from the given values of lambda, d, n, and L. And for destructive interference, once again, it'll be d sine theta is equal to n plus half lambda. So n here is equal to 0, 1, 2. So one thing you need to remember, whether it is a double slit diffraction or a multiple one, it's a diffraction grating. I would say the only formula that you need to remember if you want to answer questions is this one, which is d sine theta is equal to n lambda, and the sine theta is always y over L. The y is the distance from the central maximum to the first order maximum, and L is the distance from the slit to the screen. So these two are enough for you to get any equation from this and solve. So for destructive one, you have to put n plus half instead of n. So with the double slit diffraction experiment, we used a monochromatic light which has got only a single wavelength. What happens if we use a white light? White light has got different colors with different wavelengths. So as you can see here, the red light bends more and the blue lights bends less. The equation we derived previously for the double slit diffraction says that the amount of diffraction, that means the distance of the first order, second order max, and the distance between them, it depends on lambda. If lambda increases, that increases. So red light obviously have a bigger wavelength compared to blue. So that means we have a bigger value for y. But interestingly, if you look at refraction, not diffraction, so refraction, a white light going through a prism, in that case, red light bends smaller compared to the violet or the blue. Why is that? Because that's the behavior of refraction in dense mediums where the smaller wavelengths, that is blue and all violet, they bend more compared to red with a bigger wavelength. So it's important to differentiate these two. In diffraction, that the waves with bigger wavelength bends more, but in a prism where we use refraction, the waves with smaller wavelength bends more. But we use both ways to get the spectrum of white light, or any continuous spectrum. We can use these, either use a diffraction mechanism, or we can use a refraction or prism. So we use both devices in spectrometers to look at the spectrum. Okay, so in this question that we were talking about a wave with 132 nanometer and a slit of width 0.1 millimeter and distance 2 meter. So the one we looked at the double diffraction, where we have got two slits and interference by waves going through that, and this is D and this is L and this is Y. So we got this equation d sine theta is equal to n lambda for constructive interference. The constructive interference, there's another word for it, is an anti-nodes, because where it's maximum anti-nodes. But in this question, we're talking about just one slit. So that means there's only one slit. So how do we do that? So when there's one slit, actually what happens is that the point here, the point here, and the point here, they will act as two different slits. So that means there's going to be a constructive interference between those two. So in that case, our D is this one. So that also d sine theta is equal to n lambda. So we're going to have use the same equation, but the only difference is in this case the d is between these two. Here the d is between the 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 edges of the slit width. So now all the equations are going to be the same. So sine theta is going to be here this divided by this. That is L. So sine theta is y over L. So n is equal to 1. We're going to look at the first order maximum. And lambda is equal to 532 minus 10 to the power 9 meter, because it's nanometer. And what else we know? L is equal to 2 meter. So we are going to write this equation here. D sine theta is y over L. That means dy over L is equal to n lambda. So n is 1, so it's going to be lambda. So y is equal to L lambda divided by d. So y is equal to um, L is 2 meter and lambda is equal to 532 times 10 to the power minus 9 meter divided by d is equal to 1 times 10 to the power minus 4 meter. So 1.06 minus 10 to the power minus 2 meter. That means the antinodes, we can say antinodes are 1.06 times 10 to the power minus 2 meter apart. So you can use the word antinodes, or they are the max.